Okay, I can start?
Yeah, please go ahead.
Okay, thank you. Good afternoon, everyone. My name is Fernando Sirumbal. I am now structural engineering, doing structural engineering at POIDI. So I'm with power energy projects, which is related with the topic to discuss today. Previously, I have a stage in TNO Diana in TU Delft. And I work in this topic that is the HFTD method that I am very pleased to explain today, and I hope every one of you find it useful for your own work, right? I do some kind of academic work also related with the finite element method and numerical methods applied to engineering, but more of this work is related with structural dynamics and more specifically in earthquake engineering. So this is the title of the presentation is Seismic Analysis of Dams using the HFTD method. And the first thing I would like to show you is this picture of 4 different dams, real dams, where we can find the 3 main components of this kind of systems. In these photos, what we can appreciate is that we have the terrain, we have the water, and also the structure. These 3 components interact together and are the main key element studies for this type of analysis. If we choose to do a model, we have several options, right? And for example, this is one of them. This is a simple one, but it's one that is commonly used, mostly in the professional practice when we want to do something that is quick and not so elaborated to have a preliminary idea of what is the behavior of this kind of systems. We may choose to do a 2D finite element model, right? And then we manage to have the 3 elements that we saw previously: the foundation, the structure or the dam, and the fluid. And if we want to do seismic analysis, we have a source of vibration. These are the earthquake waves that start in some part inside the earth, and these waves propagate as we can see in the symbol of the red circles. These waves eventually go to the surface of the earth and hit the structures that are founded, which foundation is in the surface, right? This generates vibrations in the structure. In this particular case, in the dam. And the dam, when vibrates, generates waves in the fluid that is in contact with the dam. In this particular case, right? So we have that the terrain transmit the vibration through the waves, through the propagating waves, to the base of the structure. The structure starts to vibration, and this vibration generates waves again in the water, and the water generates again a reflection of these waves to the face of the dam. So we have some kind of complex interaction between the 3 components, and what we are going to do, or we are going to try to explain, is a way to modulate this kind of system. To do that, you have to make some assumptions. These assumptions are with the main purpose of making the solution of the problem possible and not so complicated. as we are civil engineers, our main purpose is to model with as soon as possible the we are going to design, right? But in the case of the fluid, we do not need to model it with the default assumptions. So we can kind of limit the assumptions we do or we make for the fluid, right? And the first assumption that is done in this method is that the fluid motions or the displacement amplitudes of the fluid are small. The velocity magnitudes of the fluid are small also, and that this is a kind of inviscid fluid like could be water which viscous effects are not necessarily considered. And the compressibility is something that is important to have in mind, but in a small per. So this means that the variation of the density is accepted as an important key to take into account, but this variation has to be small. And the last assumption is that the body forces in the fluid are not taken into account in the formulation of the equation of motion of the fluid. It's could be taken into account as an applied force to the terrain or to the dam, but not as part of the equation of motion of the water. So with this, with all these assumptions, we can have a very simplified but important and interesting for our purposes formulation of the wave equation of the fluid. We have a very reduced or simplified version of the Navier-Stokes equation, which relates the accelerations in the fluid with the variation or the gradient of pressures in the fluid domain. We have, on the other hand, a second equation, which is the linearized continuity or mass conservation, which relates the divergence of the velocity of the fluid with the variation of the density in time, which is related with compressibility, as we discussed previously. And the third is the constitutive equation or elastic deformation, which relates the variation of pressure in time with the variation of density in time. This is by means of the bulk modulus that is for the liquids, in this case for the water. The mix of these three relations is used to obtain the acoustic equation or wave equation of the fluid, which is the one that we can see in the lower part, and which relates second derivative in space Laplacian of the pressure of the water with the second derivative in time of the pressure of the water. So we can see clearly here that the equation of motion of the water is defined in terms of its pressures. It's related by the velocity wave that we can see, which definition is there in terms of the bulk modulus and the density of the water. This is the classical scalar wave. We could have previous application or topics.
Fernando, can you hear me?
Yes.
If you click on the screen, then you can get rid of this taskbar, and also you have a full control of your mouse, so you can directly indicate the equation that you are using and talking about. Thank you.
Okay, perfect. Okay, sorry. So we continue now. based on this previous scalar wave scalar equation, we have now to define boundaries of the boundary of the fluid domain. The fluid domain is this cyan rectangle we see in the figure, and we have four boundaries: top, bottom, left, and right. And we can define it in two cases. We've chosen to explain or to show two ways we can define this boundary. The first case is that we consider that the fluid is incompressible. Is the most simplified way of define the fluid equation of motion, and in this case the pressure in the top is set to 0, the pressure in the left boundary is set to 0 also, and the gradient of the bottom is set to 0 also. This means that we have an incompressible fluid, and the far field, that is the left boundary, is set to 0 dynamic pressure, the top as well, and the bottom part is fully reflective. So the waves that hit the bottom of the fluid are reflected in the opposite direction. There is no surface waves, and this is a classic added mass system. You've worked previously with this kind of Westergaard approach. This is a kind of added mass system. This means that the whole influence of the fluid in the structure is reduced to an additional mass, right? And this is the case. But when we have the compressible fluid case, the second case we're going to present here, we have a velocity wave definition that is not infinite in the previous case, but is a real number that in the case of water is around 1,400 and something meters per second. And again, we can have the top of the boundaries set equal to 0, but in the left side we have a far field non-reflecting boundary. So this is a boundary that absorbs the waves, so does not allow the waves to go back to the system, right? And is defined in terms of the gradient of pressure and the velocity of pressure and the wave velocity of the fluid. And in the bottom part of the domain of the fluid domain, we have a similar type of a bottom absorption, the similar field, but with the difference that we have this factor alpha that allows us to manage how much part of the waves we want to reflect and how much part we want to absorb. So these more elaborated boundary definitions are subject to consider that the water is compressible, as you can see. This system is called a frequency-dependent system, and we will see that it's not only mass addition, but there is another component that we are going to check. Now, in both of the previous case, I have explained the right side boundary has not been explained, because this is the most important boundary. This is the one that makes the connection with the dam. So this right boundary has to be explained with more detail. As you can see in the figure, we have an interface between the dam and the reservoir. This interface in a 3D model is a surface, in a 2D model is just a line, but this interface has to be defined because the interaction of the two domains, fluid and solid, is governed by this definition. So we have two equations. Equilibrium is the first equation. This equation mainly says that the tractions applied to the solid can be related with the hydrodynamic pressures that are in this line, in this interface. So it's the equation we can see in the left side. And the continued equation with this in the right side is a kinematic relation that relates the movement of the particles of water in this line with the particles of solid or the solid particles of the dam in the same interface surface. And it says obviously that the velocity of the water particles has to be equal to the velocity of the dam particle times the normal vector to the surface. This is a scalar product, and we have a scalar condition of continuity. This continuity equation can be reformulated in such a way that we have not velocities of fluid, but the fluid part defined in terms of pressure. For doing this, we use again the Navier-Stokes equation we present previously, and we use this equation by means of a derivation in space and combined with or replacing the continuity equation, and we finally get the dynamic fluid structure interaction relation that simply says that the gradient of the pressure is equal to minus the density of the water times the scalar product of the normal vector of the interface surface and the acceleration of the particles of the dam in the same surface. So we have a relation of pressure with acceleration. Now we have again the continuity equation, but reformulated in this way, and these two equations are going to be in the definition of the equation of motion of the fluid domain and in the equation of motion of the solid domain. In both equations, we are going to see the presence of these fluid structure interaction conditions, which is important to keep in mind. So now we have the full picture complete, right? We have the reservoir, the wave scalar equation, which defines the equation of motion of the body of the fluid domain, and we have the relations which explain how is the behavior in the boundaries, in the far boundaries of the fluid domain. And in the right hand side, we can now find the continued equation of the fluid structure interaction. This way of definition we call in finite element method we call weak form, because it's a continuous form which defines the equation of motion or of all the particles inside a domain we want to study. Is a strong formulation because these equations are valid for all the points. But when we do finite element method, we want to get a discrete definition of the problem, and for that we use different procedures like the Galerkin method, for example, to transform this point-by-point definition of the equation in a volume or body equation in a general way. For doing this, we use the shape functions method. We this is the domain which is continuous into a domain which is defined in several points of a mesh, right? When we do that and use a Galerkin method, for example, we can arrive to this kind of equation in which we have a matrix multiplied the second derivative of a vector, the second derivative of time of a vector plus another matrix which is which is multiplied times the first derivative of the pressure vector, and so on. And these matrices are called MF, CF, and KF just for have a kind of relationship with with the classical definition of a solid equation of motion, a dynamic solid equation of motion. The real definition is not a kind of mass of a damping matrix, but this is what we see in the expressions, right? This is all of these matrices contains the definition of the boundaries and contains the definition of the scalar wave equation of the total domain. And the fourth element in the equation, as you can see, is the element that defines the interaction with the solid. We can find here that the mass density of the water is multiply a matrix R that is called interaction matrix. I'm going to explain what is this, and times the second derivative of the displacement of the dam. So this is a kind of coupled equation which is defined in terms of two variables: the pressures and the accelerations of the solid. The same with the solid part as we usually do for doing any kind of analysis which is not a fluid structure interaction but just a structure. We could see that the continuous variable that is displacement here can be defined again in terms of a discrete vector of displacement times a shape function matrix. This could be replaced in the equation, and we have the classical dynamic structure equation that is in terms of mass damping, and in this case not in terms of stiffness matrix, because if we want to do something nonlinear we have an internal force vector which is dependent of mainly, or in most of the cases, of time, displacements and velocities. And in the right hand side we apply force and again the interaction term, which is the influence of the pressure in the interface surface of the dam times this interaction matrix that I'm going to explain now. The interaction matrix, what is this interaction matrix? It's just a matrix that allows us to relate the pressure vector in the nodes in the interface, but that belong to the fluid, with the forces that are equivalent in the same interface area or surface, but applied as nodal vectors to the solid part. No, so this depends, as we can see here, of the shape matrix for the fluid domain and the shape matrix for the solid domain vector to the surface which is changing point by point. So in the scheme that we can see in the bottom part of the slide, we can see that we have two finite elements connecting in the interface. One is the finite element belonging to the fluid, and the other is the finite element of the solid. Okay, and now we have to relate the pressures in the nodes of the fluid with the applied or equivalent applied forces in the nodes of the solid, right? This is done by means of the interaction matrix, which is calculated numerically as this integral over the surface. So now we have the two equations, right? The one that is the definition of the equation of motion, the discrete equation of motion of the fluid, terms, pressures, variables, and we have the equation of motion of the solid domain, or the dam in this case, in terms of displacement variables. And in both cases we have the influence of one into the other, right? That's why we have a kind of two set of equations with two variables, and both of them are coupled. And the question now is how we can solve this kind of equations. Initially, the classical time or direct integration methods we use for a normal dynamic problem is not possible to be used here, because these methods are just are formulated usually for one variable. So it, a term, or if we didn't have this term that is dependent on another variable different than the one of the domain, we could use the Newmark or the Euler or the times or the Hughes-Taylor method, but in this case now it's not possible to do it directly. We could do it in a kind of iterative manner in which we assume a first pressure vector in the second equation, and we introduce this kind of initial approximation, and we solve it just as a solid domain equation, and we get a displacement vector that we replace in the first equation of the fluid, and again solve it to find another pressure vector, and do it this procedure several times, going from one equation to the other to finally find the two set of vectors. But this could take so much time, and it's not it's time consuming. It's not so efficient way to do that. We can see that these kind of problems are directly and nicely solved in the frequency domain, not in the time domain. In the frequency domain, what we do is we express the variables in terms of the one moment please. Okay, sorry. We express the displacement vector and the pressure vector in terms of its harmonic by means of the Fourier series, and we do the same with the external applied force, and we replace it in the previous equation that is reproduced here, and we obtain the frequency domain equivalent equation for that expression. This is for the solid, and if we do this, okay, sorry, this is for the fluid, and we obtain an explicit equation that relates the pressure amplitude in terms of the frequencies of vibration, of excitation, with the displacement complex amplitude. So we have an explicit relation obtained just from the first equation, from the equation of the fluid, and this is in terms of a matrix HF, which is in terms of the excitation frequencies and of the matrices that define the fluid domain in the equation. This means that we now can replace this pressure amplitude into the solid equation directly that is shown in this slide, and after doing this we can rearrange the equation, the solid equation, and we will notice that at the end we manage to have finally the solid domain equation in terms only of the displacement amplitude. So this is the solution in the frequency domain. And the most interesting thing of this approach is we can clearly see that the influence of the fluid over the solid domain can be understood as an additional mass introduced to the system and an additional damping introduced to the system. This additional mass is the real part of the multiplication of the interaction matrices times this HF matrix, which is frequency dependent, and the additional damping, on the other hand, is the imaginary part of the same matrix multiplication times the density and the excitation frequency, right? So we have to understand and keep in mind that this kind of solution allows us to understand that the fluid structure interaction functions in a way that introduce mass and introduce damping to the system, to the damp equation, to the damp equation of motion, right? And this frequency-dependent system, totally frequency-dependent system, dependent of this HF matrix, depends of frequency-dependent properties, obviously. And if we want to know which is the source of these frequency-dependent properties, we can just do a simple exercise, that is, assume that the matrix M of the fluid is equal to 0, is a null matrix, and the C matrix of the fluid is equal to 0, and we will have that HF is just only the matrix K of the fluid, the inverse of the matrix K of the fluid, no more than that. And there is no more frequency-dependent presence in the HF term. So when we calculate the additional mass with this HF, this particular HF, we can notice that the additional mass is not frequency dependent anymore, and the additional damping is equal to 0. So we have a simplified version in which the mass, the influence of the fluid over on the solid part of the domain is just additional mass, pure additional mass, which is not anymore dependent of the frequency of excitation, and there is no additional damping. This is the simplified equation that appears when we assume that there is no compressibility. So the first main conclusion we can take from this is that the compressibility is one of the source of frequency dependency of this kind of fluid structure interaction system. And the bottom absorption, all the absorption boundaries are also part of this frequency dependency. So we have a frequency dependent system, and we have maybe some non-linearities that we want to include in the definition of the fluid, of the solid behavior. How can we deal with these two type of characteristics of a system? Because we know that the frequency dependent solution that we have just showed is only valid for linear systems. If we want to do at the same time nonlinear systems, we have the hybrid frequency time domain method, that is the method that allows to do this, and this is the importance or the convenience of using and learn how to use this method. So the reason why we choose HFTD is we take the most interesting things of both ways of solution of an equation, in the frequency and in the time domain. In the frequency domain, we can obviously take into account frequency-dependent system, but it's just valid for linear elastic analysis. And we have another drawback, that we obtain only frequency response plots that are not so friendly to process the data, to understand the analysis of results. But in the time domain, we can do nonlinear analysis, and the output can be time history plots that are more friendly to show when we want to know the results of our analysis, right? So we combine these two types of methods, and we can do HFTD. To do HFTD, apply to seismic analysis with an acceleration, with a ground acceleration, we have to do some modifications in the last equation of the solid that we've presented previously. First of all, we have to introduce the ground acceleration in the right-hand side and express the equation in terms of relative coordinates, as we usually do. So this is the first step, is done in this slide. And the second is that the nonlinear internal force has to be tackled by means of the pseudo-force concept. The pseudo-force concept is express the nonlinear internal force in terms of a linear internal force minus a pseudo-force, that is the Q vector. both vectors are introduced in the equation, and we find that these expressions for the same equation is just a different way of express it, but with the advantage that in the left hand side we have the classical linear definition of the problem, and in the right hand side we have the ground acceleration, we have the interaction term, and the third term, that is the pseudo force vector that is obtained iteratively by means of a iteration procedure, right? This equation can be expressed again in terms of the frequency domain analysis, which is what we saw that is the most direct way of solving this, and we can use the way that we can uncouple this by expressing the pressure amplitude in terms of the frequencies of excitation. This pressure vector can be replaced in the equation, and finally we obtain the last equation we can see in the bottom part of the slide, and we see again the added mass and the added damping terms, but we can see in the right hand side that we have added terms too in the same way of added mass and added damping that is applied now in the multiplication of the ground acceleration. So this relative coordinated formulation has these additional terms. Now the HFTD has another advantage, that is that we can use the mode superposition method in the way that is shown in this slide, right? So it is just required to express the amplitude, the complex amplitude of the displacements in terms of a mode-shaped matrix and coordinates, and after replacing in the previous equation, we obtain this simplified equation in which all the matrices are generalized matrices and depends on the mode shapes of the structure, of the linear mode shapes of the structure, right? I have to say that not all of these matrices are diagonal. Most of them are banded matrices, so we cannot just solve this equation totally uncoupled one by one, right? We have to keep what we have here is a reduced equation. We pass from an n times n system to a number of modes times number of mode systems, depending on the number of modes we want to include in the solution of this equation. And the other thing is that we require to express the right-hand side terms that comes obviously in the time domain. The signal of the ground acceleration of an earthquake comes usually as a time signal, and we have to express it in terms of frequency domain because we are going to solve it in this domain. And these are the expressions we use, that these are the discrete Fourier the discrete Fourier method for obtaining a time series in a frequency point, right? And this has to be done for the acceleration, and has to be done for the pseudo force, and has to be done for the force. See there, but we use an extended Fourier period that is not the extension of the signal only, but is bigger than that. This extended Fourier period is used because we want to simulate the transient response. We want to take the transient response of the system and not a kind of harmonic response of the signal repeated several times. For doing this, we have to calculate this extended Fourier period that with expressions we can see in the bottom part of the slide in terms of the first fundamental period of vibration of the system and the damping ratio of the system. This is the difference of a time signal that is processed with Fourier transform, just using a period equal to the signal length, and in the second case using a Fourier period that is 10 times the signal length. And we can see that the spectra we obtain are different, right? So this is important to be done. We have to be sure that calculate the correct extended Fourier period. And finally, the time segmentation approach of the HFTD makes it possible to solve the equation point by point inside a time segment. For example, time segment K is divided into several time points, and we solved only the solution of this time segment, and only after we finish to find the convergence in all the segments in all the points of the segment. To do that, we kind of modified the input signal in each segment in such a way that the signal after the segment is cut and an appended decay function is added in order to obtain the solution without too many iterations. And this is HFTD in Diana. This is the conclusion or the big picture of what we explained. In Diana, the first step is evaluate the model. After that, Diana does an eigenanalysis where we obtain the eigenfrequencies, the generalized at mass, the at damping, and the load. And when we have all these matrices and terms, we can do the fast Fourier transformation to obtain the gradation and the pseudo force in terms of the frequency domain. And after that, we solve this pseudo-linear equation in the frequency domain. And when we find the solution in the frequency domain, we use the inverse fast Fourier transform to translate it to the time domain and calculate a new pseudo force that is the difference between the previous one in the previous iteration. Once we have a new pseudo force, we do the process again until we get convergence. Now we get to the case studies. I'm going to present two case studies, one in 2D and one in 3D. And these case studies have been performed using Diana. And the first one is this 2D model. A transient analysis is to structure interaction model, and linear and nonlinear properties have been considered for this case study. The first case, we do not consider the presence of water, which is the most extreme and unrealistic case. The second is considered water, but just as incompressible, and the third one is considered water, but with compressibility and therefore frequency-dependent properties. The results we obtain in the first incompressible fluid case for a linear elastic behavior is that when we use Newmark and HFTD, we obtain almost the same results, which is important to be checked, to know that the HFTD is correctly or is precise enough when we don't have to deal with frequency-dependent properties. That's why we can compare with Newmark, because Newmark could not do the work for the frequency-dependent system. And for displacement and acceleration, we obtain a very good agreement between both methods. This is just pictures of different time steps, and this can give us an important idea of how the hydrodynamic pressure changes in any time step of the time history results. the shapes are variable. The directions of the application of the pressure could be towards the dam or in the opposite direction. It's very, very variable, so it's important to know that the pressure distribution is not something we can simplify it in a precise way. When we do nonlinear, when we consider nonlinear behavior of the dam, for example, cracking behavior of the dam, now the solution is not so similar when we use HFTD and Newmark. And this is because Newmark uses the whole set or the whole package of equations, considers all the modes of vibration because it's a direct integration method, whereas HFTD uses the modal reduction method, and this has a kind of impact when we do nonlinear analysis, obviously. What we can see here is that the cracking pattern of both methods is totally different. In the Newmark, we have a big crack in the base, whereas the big cracks are not in the base but in the interface phase with the fluid, right? And this is because no matter than the displacement contour for both methods are almost the same, as you can see in the first figure. When we look at the principal strains, we notice obviously that the concentrations of strain for the Newmark is very, very high compared with the concentration of strain in the HFTD, where it's more sparse, more distributed. And this is related, as I explained previously, it depends of the modal reduction we do in HFTD. And obviously, when we have a big crack for the HFTD, the energy absorption of the system is bigger, and therefore the amplitudes of the displacement in the crest of the dam is diminished in the case of the Newmark analysis, whereas in the HFTD there is not too much energy absorption because of nonlinearities, loss of energy, and we have that the displacement, the lateral displacement of the crest is almost keep invariable or not reduced too much. Now we are going to present the influence of fluid compressibility in the response of this kind of 2D finite element models. This is again the displacement of the crest in the x or lateral direction, and we compare the model without water, the model with compressible water, and the model with incompressible water. What we can see is that when we just do not consider or neglect the influence of water, the displacement we obtain are very, very low, and this is dangerous if we want to do an analysis without considering explicitly the interaction with the fluid, because we are going to have displacement that are less than half or the real displacement we could find in a real earthquake event, right? The difference between incompressible and compressible for this case, that is a simplified 2D case where the water maybe has not so big influence, is not so clear, but what we can see is that the peaks of the compressible case are a little bit bigger in all the cases. But we have to now be clear that the difference exists between these two approaches. When we do the same for nonlinear cracking, just using HFTD, we can see that the patterns of cracking are obviously different. In the empty reservoir, almost there is no cracking, and when compared with compressible and incompressible, we can see that the concentration of cracking is more in the toe of the dam, in the upstream direction, in the case of the compressible case, whereas in the incompressible case is more distributed over all the interface. Finally, the 3D case study. This is a real model we did in the Llana, and we can see the terrain and the dam and the water, right? These are the components. We have the foundation that has these geometrical properties of height, length, and width. It's a very big model. All of them are built with solid 3D type of the Llana finite element, with the exception of the fluid that it has in the Llana a special finite element that is the flow 3D. Okay, the height of the dam is 220 meters, and the width in the top is 430. That is a lot, and the length of the reservoir was decided to be of 500 meters. The number of elements is shown in the table in the bottom of the slide, and the number of nodes also. We have the material properties for the concrete dam, the modulus elasticity, Poisson ratio, density, and the Rayleigh damping parameters we used for modeling the damping of the concrete dam. In the case of the reservoir fluid, we have to define what is the sonic speed, or the C, the density, the wave reflection for infinite extent boundary, and the wave reflection for bottom absorption boundary. The modulus of elasticity of the soil foundation, the Poisson ratio, and the density 0, because we just want to model the stiffness of the foundation and not the vibration properties of this foundation soil. So the first thing or results I can show you is the modes of vibration. This modes of vibration is taking into account the additional mass given. So in the simplified incompressible equation of motion, if you remember, we have an added mass and no damping, right? This same approach is used here, and with this added mass, it's solve the eigenvalue analysis, the eigen problem, and we find the modes shapes and the frequency of each of them. This is for the first 4 modes, and these are for from mode 5 to mode 8, and the last 2 modes that we are going to present here. And an important fact here is that the mass of the structure, say the mass of the dam, is 4.7 times 10 power 9 kilograms, and the added mass given by the fluid is 6.41. This means that the fluid added mass is more than the original mass of the structure, in this case, which is a 3D model, where the water has a bigger impact in the movement of the dam, and this fluid added mass is equal to 136% of the structural mass. So this is quite a lot, and this is something we have to take into account. Again, when we do the comparison of the incompressible case to be able to compare with Newmark, the incompressible case with HFTD, we obtain very, very good agreement between both methods in the linear case. And when we try to introduce the frequency-dependent property, that is the compressible of the water, the radiation boundaries in the left side and the radiation boundaries in the bottom, the different are notorious here. Is something we can see easily, right? In the compressible case, there is because of the radiation boundaries, there is energy that is taken out of the system, and therefore the amplitudes of the vibration in the crest of the dam are reduced. This is something we could not see if we do not take into account the frequency-dependent properties of this kind of fluid structure interaction systems. The vertical stresses are compared for the incompressible and compressible case. in the left column we find the incompressible case in the vertical stresses over the height of the red line we can see in the left side of the slide. We have that the blue one immune stresses we find through all the height in the whole history of the simulation. The green one is the static one, or the starting point of stresses, and the red one is the maximum, right? In the left side we have the incompressible cases, and in the right side we have the compressible cases. For both cases we have the stresses in the upstream section, so it's the phase in contact with the water, and the downstream section, which is the phase in the opposite side of the dam. What we can see here in this case is the vertical stresses are increased when we use the compressible assumptions, right? And this is important to be taken into account. If we decide to just use an added mass approach, we are missing some additional vertical stresses that could be decisive in the design of our dam. The hub stresses are presented in a similar way, and here we can see that it's the opposite of the previous case. In the incompressible case, we obtain hub stresses that are bigger than in the compressible case, and this could have the opposite effect of having a too conservative design, right? If we don't consider the compressible or the frequency dependent terms. The radial displacement is more similar in both cases, but again it's not totally the same, right? We have that in the compressible case, the maximum displacement are a little bit higher than in the compressible case, but it's not so much. And as a conclusion, this is the final slide of the presentation, is that the HFTD analysis is available in the standard Diana version. It's something you can use if you want to do this kind of models with higher precision. And the HFTD and Newmark methods is proved to give the similar results for frequency dependent system, and the HFTD has the additional advantage that can quantify the effect of frequency dependency of the reservoir, the bottom absorption, the far field boundary, that are called the frequency dependent properties of the system. Okay, this was the presentation. I hope I could be clear enough and that you are interested and eager to learn this new feature of Diana that is important when you try to design dams or any kind of structure in contact with water. So it's a very interesting feature, and I am here to answer any question you can have due to the presentation I just realized. Thank you very much.